Hello everyone, welcome to this session. I am Saptarshi Mukherjee. This is a bit about myself. I'm a software engineer 3 at Google, and in short, I've been a competitive programmer for a good time. So, in this session, I'm going to focus on a quite important competitive programming topic, which is DP on trees, dynamic programming on trees. So, over the last few contests, I actually made some observations that this is a really important topic which will help you improve your programming and your performance in these contests. Uh, Following that discussion on DP on trees, I'll be coming to this question, which is a hard problem that came up in educational round 162 recently. So I took part in that contest and I could solve 5 problems out of 6. This is the fifth problem, problem E, and it's slightly a hard problem based on this topic DP on trees. So we'll be discussing this problem right after the discussion on the topic DP on trees. So let's get started. Before I get started, this is my official ID of Codeforces. I got a 73 rating increase, and I'm looking forward to again restoring my ratings of a candidate master and a master in the coming coming contests. So yeah, you can follow me there, and I hope you would wish me luck. So anyway, let's get started on the topic. This is dynamic programming, which we are going to discuss on. What I noticed is that in the recent contests, if I have to mention one topic which is super important for actually getting to the levels of expert, candidate, master, and above, then this is that topic where you have to excel. This is not just based on the previous contest, but also on my overall experience of competitive programming. And theoretically, we express it in this way that any problem which has an optimal substructure and overlapping subproblems classifies as a dynamic programming problem or dynamic programming solution. I will not go much into the theoretical aspect, but I'll mention one thing in short. The dynamic programming basically is a very principal technique on the application of recurrences. So, what does recurrence actually mean? It is something like when we say Fibonacci of 5 is equal to Fibonacci of 4 plus Fibonacci of 3. You can look up Fibonacci numbers. This basically is recurrence when we say that we can solve a bigger problem from the solutions of smaller problems. So here, if I know the solutions of Fib 4 and Fib 3, I can find out Fib 5. So that basically helps me to generalize, saying that Fib of n is equal to Fib of n minus 1 plus Fib of n minus 2. This is a very specific problem, but the high level problem of dynamic programming is that if you know the solutions for smaller parts of the problem, known as subproblems, you can easily find the solution to bigger problems. So, now what I noticed on top of it is that in the remaining, in this recent contests, these are few topics that actually had a greater frequency. So first of all, I found this particular thing of DP, select or not select. I stressed on it in one of my previous videos, blocking elements. There are other videos as well, but this video you can find in the linked in the description, and you can basically take a look at it. This is one Codeforces, I think, D problem, which I had discussed around a month back, if I'm not wrong. So other than this, you have some classical problems as well, like longest increasing subsequence. You can take a look at this. This is a very fundamental topic of dynamic programming, which you should be aware of, which you should be proficient in. And now this DP on trees is basically taking that particular approach to a different dimension. We say now we have to use it on a non-linear data structure, non-linear data structure trees. So it is the same thing, but slightly with a different dimension. We have to move up and down in some ways. So this is what we are going to focus on in this particular session. So let's get started. This is the question I'm going to start with. Given a tree of n nodes, you have n nodes. Each node I contains AI coins. Ith node contains AI coins. Now choose a subset of nodes. So you have to choose some nodes such that no two chosen nodes are adjacent. So if you are choosing some nodes, no two of them should be adjacent. In other words, you cannot choose any two adjacent nodes together. If two nodes are adjacent, you can choose maximum one of them, not both. That is the first condition, no two are adjacent. What is the second condition? Sum of coins in the chosen nodes is the maximum. Very common kind of a problem. This is a maximization problem. You have to maximize the sum of the coins, and you cannot choose all the nodes. There you have a blocking criteria. So sum of coins has to be maximized. Now this makes it clear that okay, you have to choose some of them and you have to maximize something. You cannot choose all of them due to the first condition. First condition tells you choose as less as possible so that there is no conflict. Second condition tells you choose as many as possible so that you have it maximized. So somewhere maximization tells you as much as possible, which means this is what you have to focus on, keeping this in mind. This is a precautionary thing. This is a kind of blocker, a limit on that. So you have to take this up, keeping this under control. That is the high level idea. Okay, now let us see some examples and then we will discuss approaches. First of all, this example. I want to maximize the coins, the number of coins. Let's say this has 2 coins, this has 4 coins. So the value I'm writing inside the node is the number of coins. So what can I say? If I choose both of them, there is a maximum, but can I choose both of them? No. By the way, it is given that AI is always greater than, let's say it is given that given AI is greater than equal to 0, let's say greater than 0 for all I. Okay. So what I can say over here is if I choose both of them, that is the best, but I cannot choose due to the first condition. These two are adjacent, so I cannot choose both of them. Which one will I choose? The greater one, so that the sum is maximum. So I will choose the greater one. Now, to the same tree, if I have another node attached over here, now will 4 be my answer, the greatest one? No, here we can see that the two smallest ones together can be a better answer. If I choose 4, I cannot choose 2, I cannot choose 3. If I choose 2, I can choose 3 together. So 2 plus 3 gives me 5. So this is the answer. Now slightly bigger one. Over here, I can say 2, 3 gives me 5. Together with it, I can choose 5. So this gives me 10. If I don't choose them, if let's say I choose this 4, the only option for me together with 4 is this 3. So I can say that the yellow is winning over here. So the yellow will be a better choice over here. The light yellow, the sky yellows, this together with this and this will give me 10. Whereas 4 and 3 will give me only 7. Now if I slightly increase it, or if I slightly change it from this 3 to 7, up to here what we notice is that okay, either these even levels or these odd levels will be the answer, right? This can be one strategy in your mind, that I'll have this kind of a tree, something like this. So I will choose either all the even levels or I will choose all the odd levels, basically alternate level kind of strategy. But this is one example where you can actually see that approach will not work. If I choose alternate levels, I have 2, 3 and 5 basically making it 10, and I have 4 and 7 making it 11. So if I choose this one, basically this is 11. But can we not have a better answer? If we choose 2 and 3 and then if we choose 7, that gives me 12. So this is the best answer. So here are we choosing alternate levels? No. Are we choosing every level entirely? No. I'm not choosing this level entirely. I'm only choosing this level partially. So there is no such pattern that okay, in this way only my entire problem gets solved. Only in this selection, these are the 2 types of selection, I just look at both the selections and I'm done. No. Each node may or may not be chosen. So if I basically look at the possibilities, my total number of subsets, the total number of subsets is equal to 2 to the power n. Not all of them are valid, but this is the total number. If I ask non-empty subsets, that is 2 to the power n. minus 1. But this is the total number of subsets, and for each of them, if I have to see, I cannot solve it for some big values like n going to 10 to the power 5. Usually for this problem, n can go to 10 to the power 5. So 2 to the power n is out of the question. I have to think something like big O n or maximum big O n log n. So how to solve this problem? Now, before I proceed to the approaches for this problem, we have a very similar problem, which I think is known as CoinDP. That is a 1D problem. That how do you solve the same problem for an array? Let's say if you have some array, you cannot choose adjacent elements. So array of basically each element contains number of coins. So again, if you have something like this, 2, 3, 5, 2, 1, 4, 2, 3. Then probably somewhat like this, you can say here, choosing this 5 and choosing this 2, 3 is the same thing. Let me make it a bit bigger so that this is more interesting. Maybe something like 7. So I can say, okay, this 2 and this 7, and then I can focus straight away on this 4 and then on this 3. This looks to be the best choice. So over here, one approach, the very common approach, market approach basically is that I will remember up to each index what is the best. Up to each index what is the best. So I can say, okay, up to the first index, 2 is the best. Then I can say, okay, 3 cannot take 2, and before 2 you have nothing. So that is equivalent to 0. Answer before the 2 is 0. And DP basically represents something like max till now. So 3 can basically look at this value or anything before that. 3 plus 0 gives us 3. Then 7 can say, okay, this or this one, anything, whichever is the maximum. 7 plus 2 gives me 9. Now 2. 2 plus 3 gives me 5. But I can say that 9 is better. So somewhere we can express this answer as the maximization of if we are taken versus if we are not taken. What is the best answer if we are taken versus we are not taken? So if this guy is not taken, then we find the best answer, which is 9 over here. If we just remember that, then there is a problem. If we just remember that, then somewhere if later on I'm asked, hey, by including you, what is the best answer? I'll fall in trouble over there, if that is somewhere the case. So one common approach is, because we are looking for two cases, when ith element is there and when the ith element is not there, we make two different DP states for that. We make two different DP states for that, DP1 and DP2. DP1 basically is ith element chosen, and this one is ith element not chosen. Let us see the advantage here. For 2, if it is chosen, we have 2. If it is not chosen, we have 0. For 3, if it is chosen, before 3, if it is chosen, we can directly say, hey, previous element cannot be chosen. So what is the maximum for the previous element? This one directly can be used in our answer. We can directly say, hey, use it. 0 plus 3 gives us 3. And if it is not chosen, I can directly copy it. This is the maximum. If it is not chosen, I can basically say, this should be the maximum. 2 and 0. Whatever is the maximum out of them. So that gives us basically 2. Next, so what I understand is a basic DP formulation, that DP1 I is equal to the maximum answer till I if ith element is chosen. And that is going to be ARI plus dp of dp2 of I minus 1. And what is dp2? dp2 of I is equal to the maximum answer till I if ith element is not chosen. Ith element is not chosen. Sorry, is not chosen. And in that case, I can say, okay, this is going to be dp, the maximum of dp1 I minus 1 and dp2 I minus 1. So up to I minus 1, whatever is the best you have got. By choosing or not choosing I minus 1, that is going to be the maximum. If I apply it above, you can see, so this answer will come from this dp2 I minus 1 plus ARI. So dp2 I minus 1 plus ARI will give me dp1 of I. So 7 plus 2 gives me 9. I'll have 9 over here. And the maximum of these two gives me this answer, that is 3. If 7 is not chosen, then 3 is the best answer, which is correct. And now we can just keep on forming. 3 plus 2 is 5. And if I don't choose this, 9 is the best answer. See, I'm not just copying this one, or I'm not also always copying this one. Maybe we'll get some examples. Let's see. So if I have, let's say this one, if I choose this, I'll have 9 plus 1, 10. And if I don't choose this, I'll have 9. So you can see here it came from dp1. We are doing maximization of dp1 and dp2. This 9 came from dp1. However, the next 9 comes from dp2. So we are doing a maximization. That I don't want to know whether I minus 1 was taken or not taken. If I minus 2 is not taken, up to I minus 1, whatever is the maximum, I'll take that. So dp1 and dp2, separate definitions for chosen and not chosen, actually makes it easier for us to formulate. We get very simple expressions like this. The other expression can also be simple. We can think in that way, but I'm sticking to one convention in this session. So if we complete this, we'll basically have for 4 as well. 4 plus 9 is 13, and dp1 gets copied, so 10. And then over here it's 2 plus 10, that is 12, and the maximum, that is 13. And for 3, I can say here we have 13, and 13 plus 3 is 16. 13 plus 3 is 16, and then the maximum of these two is 13. So I can say that we have chosen this one in getting this 16. This 16 came from here, this 13. So we have not chosen this 2. And this 13 came from here, so we have chosen this 4. And this 13 came from this 9, so we have not chosen this 1. This 9 came from here, so we have not chosen this 2. This 9 came from here, so we have chosen this 7. So this 7 has been chosen, and then you will trace back and see this 2. So 2 plus 7 plus 4 plus 3, you can actually trace back as well. For that, you need to store one more information. With this table also, you can store it. But you just have to go back the way I actually went back. That check from where this dp1 of I or dp2 of I came from. By that, you can actually trace back and find the final solution, or find the total trace, which elements actually gave you the best answer. But so far as finding the maximum is concerned, the answer over here is the best. The answer is basically the maximum of dp n minus 1, that is the last element, 0, dp1 of n minus 1, dp2 of n minus 1. Now the big question is, this is a standard coin problem. Can you see the similarity between this problem and this problem? Can I use the same thing in the 2D version as well? When all are not at the same level, when the number of adjacent nodes is also not in control, one node can have a lot of adjacent nodes, can I use the same technique? So let us take this one and see for ourselves the same DP1 and DP2 thing I'll be using. Let's take over here. Okay. So under this tree, one thing notable over here is, I think I should mention this, that this looks like a rooted tree. This is my root. These two are the children of the root, and then they have their own children. This kind of a tree, we can call this a rooted tree kind of thing. This is basically a recursive data structure. Recursive data structure. Why so? Because the smaller trees, the subtrees themselves are also trees. And in this kind of problems, if you know the answer for smaller trees, you can find the answer for bigger trees easily. You can find the answer for the bigger tree easily if you know the answer to the smaller trees. That is the reason behind calling them recursive data structures. So let us say, okay, let's solve for the smallest trees first. What are the smallest trees? The leaves. In trees, the leaves are the smallest. So we'll use the same conventions. We will say, okay, DP1 is current node selected and DP2 is current node not selected. The expectation is the same. So smallest trees are the leaves in this particular tree. Let us find out what is DP1. DP1 is the node itself. There are 2 coins there. DP2, if you don't take this, you will have nothing else to take. In this particular tree, there is nothing else. This is the only node, so you have 0. This is just like your I equal to 0 case. For this 2, this is just that case. The DP2 will start from 0. Okay, for this 3 also I can say the same thing. DP1 is 3 and DP2 is 0. Now, this is the parent of both these nodes. This nodes that these are the answers to this particular pair of nodes. What will this 4 do? This 4 can say, hey, give me your DP1, DP2 values. Let me see. These are the conditions, these are the variables DP1 and DP2. If I don't take 4, what will I take? If I don't take 4, can I say take whatever is the maximum from here and whatever is the maximum from here? The left and right will not come in conflict. They are connected via this. So if I don't choose 4, can I say take the maximum from the left and maximum from the right? Right? So I can say, okay, the maximum from the left basically is 2 and maximum from the right is 3, so it will be 5. And DP2, if I, okay, this is DP2. If I don't take the current element 4, then I'll take the maximum from the children. So it is 2 plus 3, 5. What if I take this? If I take this, I will say, hey, if I take this, I cannot take my children. I can take their children. I cannot take them directly. So I will ask them, hey, without taking you, what is the best you have? Can I say these DP2 will come in question? Which is 0 over here, but this will come in question. So the answer would be, if I have to take myself, it will have to be 4 plus 0 plus 0. These are the DP2 values. Right? Does it seem logical? So we can formulate it in this way. The DP1 of V is equal to the A of V, number of coins of V, plus the summation of DP2 of X such that X belongs to children of V, that is whatever are under that V. So then this is the, can you see the relationship between this and this? Almost the same, just that Here we had only one adjacent element to worry about. Here there are multiple adjacent elements. So we just applied the sum. We say, okay, here we said get the best without that I minus 1. Here we are saying get the best without those x. For each of the x, get them and get the sum. So almost the same thing. So if we think first in the 1D form and then in the 2D form, it becomes so simple. Next, if I want to calculate dp2, basically saying I will not take the current element. If I don't take the current element, I'll say, okay, get the best from behind. So I can say it will be the summation of x belonging to children of v, the maximum of, it will be the summation, the maximum of dp1 of x, dp2 of x. For each x, if I have the maximum, I just have to keep on adding them, and that will give me dp2 of the current node. So if I just apply this, let us see what we get. I'll start DFS at this node, and then it will call its subproblems to get them solved. Left part is solved, okay. Next the right part. 10 will call its children, so 10 calls 4. 4 says the same thing, hey, dp1 is equal to 4, dp2 is equal to 0. 10 says, okay, dp1 is equal to current, that is 10, plus that dp2 which is 0, so it will be 10, and dp2 will be equal to the maximum, the summation of the maximums, which will be 4. So dp2 is 4. Now over here, let me use a different color. I'll drag it to the left. I can say for this dp1 is going to be, take this guy, so it will be 5 plus the dp2 values, right? So dp2 here it is 5 and here it is 4. So it gives me 5 plus 4 equal to 10 plus 4, 14. And dp2 will be the summation of the maximum from the children. So the maximum from the left is 5 and maximum from the right is 10. So this gives me 50. Maximum from the left is 5, maximum from the right is 10. So this gives me 5 plus 10, 15. So basically we are saying that without taking this, we will get the best answer. How? We will get 4 and, sorry, we will get this 2, 3 and this 10. So 2, 3 gives me this 5 and 10 comes from here. So in this way, we are getting the best answer through this DP formulation. You can easily code this. Now, the thing is, we assume this is the root. Does it make any difference if I do it from any root, any other root? No, because this does not take into consideration any particular root. This algorithm is totally using the hierarchy just for checking the adjacency, just for proceeding in a certain manner. In this kind of questions, even if you have some undirected tree, you can actually take out a root from there. You can actually choose any root, select any root, and based on that, define the parent-child relationship for all the nodes. Parent-child relationship for all nodes. Nodes, node pairs, whatever you say. So if you choose, instead of this, if you choose this as the root or even this as the root, the tree will look different. For example, if you choose this as the root, then this is your root, and then the next level will contain only this node. Then the next level will contain, this is the next level, these two nodes. Then the next level contains this node, and then the next level contains this node. So in this way, the height will increase if you choose something else as the node, as the root, but the rest of the logic remains the same. If you draw it in a different way, this will look like, so if I have to choose this as the root, or let's say if I choose 4 as the root, it will look something like this. 4, under that you have 2, 3, 5, under 5 you have 10, under 10 you have another 4. In this way you have. So again, the same kind of logic applies over there. You will see that we will get the same answer, 2, 3 and 10. This is how you should get the answer. So this is the first technique that you have to sort of blindly use in such problems. So if I have to write the code, I'll simply say, let's say you have your adjacency list ADJ. This is ADJ of I contains list of vertices or list of neighbors of I, list of neighbors of I. What else? Yeah. Now I can basically call the DFS function saying that give me the those DP states. So I will call it on 0, saying that you are the root. I can use some visited kind of thing, boolean visited, which initially is all false. All are false, nothing has been visited. I'll pass this adjacent thing. This is kind of Java syntax, you can say. Then I'll basically pass this visited as well. I will pass the dp1 and the dp2. And finally, what I can say is the answer is I'll return the maximum of or math.max dp1 of 0 comma dp2 of 0. That is the root. Now this DFS function is what I have to implement. This can be void, I am not returning anything. DFS, I have a starting vertex, I have the ADJ, which in Java it will be an array of array lists, and then I will have the boolean variable viz. I will have dp1 and dp2. Okay. These are my input parameters. The first thing, I'll check that whether I have visited this already or not. Maybe it is not needed because it is a tree. Just I have to ensure that I'm not going to visit from a child. I'm not going back to the parent again through DFS. That is what I have to ensure. For that reason, the viz is needed. So I will just mark this as visited. Viz of v is equal to true. And then I'll say, okay. dp1 initially 0, fine. For I equals to 0, I okay, sorry. For int neighbors, let's name them as NHB, or we named it as x, right? So int x in adjacency of v, I will get this, that he dp1 of v means if we take this, we can say dp1 of v will start with c of v, number of coins of v or a of v, whatever. Let's say a of v. That also you can pass, or it can be global, whatever. And dp2 of v will be 0. dp1 of v is equal to, or you can say plus equal to, that is, it will get incremented by dp2 of x. You have no other option. It has to be dp2. And dp2 of v, for that you have options. You can say max of dp1x, dp2x, right? This was the formulation we got. If you reach up to here, then the only thing remaining is copy paste into the code. So the main thing for any DP relation is this recurrence relation. This is known as a recurrence relation. If you have the recurrence relation, that means you have the answer to the DP. You just have to copy paste into your code. That is it. We have the answer here. We can close this. But before this, one thing is important, that you don't go back to the parent. So before this, you will add that condition that if visited of x is true, then please return. That means it is the parent from which we came from. In a graph, probably this thing will occur always. Instead of viz, you can also pass the parent, in which case you will say, hey, if the vertex you're trying to go to is your parent, then don't go there. It can be done in different ways, but this is a simple implementation. So this is where we are basically solving our current trees based on our subtrees at every level. In this way, the span of the trees is increasing and you are gradually solving the problem for bigger and bigger trees. Time complexity, as we can see, we are visiting every node exactly once. From there, we are just propagating into all the nodes. I mean, for all the nodes, basically, okay, I missed one thing. We must do this. I missed this. Uh, where will we get these values? For these values, we need to call. We need to call this DFS function on X. X and then the adjacent C list viz dp1 dp2. Sorry for missing this. So yeah, from each node I'll call all its neighbors. So the sum of all the neighbors is basically going to be m. That is the sum of all the neighbors, and m is equal to n minus 1. We know number of edges. So the maximum number of neighbors will be n minus 1. And overall we have n nodes. So it is going to be big O of n plus m, which is n. Time complexity. The space complexity, again in the recursion stack, it can go up to big O n. Big O n space complexity. That's it. Okay. What next? Can it be done using BFS? Yes, it can be done using BFS as well. If you want to save on the recursion stack, maybe you can brainstorm a bit. You can do it level wise. That last level I'll do first, then the level before that, then the level before that. It should be very trivial. Just going back, you can just find the level or traversal and then just go back along that array and you will have all the necessary things. So I'll not go into that separately, but this is basically your DP on trees implementation. DP on trees. Now the remaining part of this session, I'll focus on the given problem. I'll tell you how you can solve it. You can take a look at the editorial also and maybe compare approaches and let me know if you found an easier approach, something easier to understand, implement, etc. But I'll tell you how I solved it using my approach. I solved it in this problem in 28 minutes, including reading the problem, finding the solution, and then implementing it. Thinking of the solution, then implementing it. So let us see what this was about. Very similar kind of a problem. N vertices numbered 1 to n. Each vertex is colored in some color, denoted by an integer from 1 to n. So there can be n different colors. A simple path is called beautiful if it contains at least 2 vertices. First and last vertices are of the same color, and no other vertex has the same color as the first vertex. Count the number of beautiful simple paths of the tree. Note that the paths are considered undirected, which means that x to y and y to x is the same thing. So basically different paths. So what is this saying? This basically is saying something like this, that hey, you have a tree, you have to find from any point to any point if there is a path, simple path, where this color and this color are the same. The start and end node of this path have the same color, and color of every node in between them is not equal to C. If every node in between has a different color and the terminals only share the same color, then this is called a beautiful simple path. We have to count all these paths. So definitely there can be many such paths. If I take each node as a starting point, that is a brute force. So if I take each node as a starting point, for each u, I find the count of u, and then I can say the answer is basically the summation of count of u for all u, count of u divided by 2. Why divide by 2? Because I'll be counting it double. Any path I'll be counting double because of the 2 nodes. One time taking this as the starting point, another time taking this as a starting point. This is a brute force, and usually when you get this kind of a problem, you can't implement this brute force. It will be of no use. So how can we solve it in an easy manner? Do we need to optimize this? The constraints will tell us that we know that there are 10 to the power 5 or 2 into 10 to the power 5 vertices, 2 lakhs, 200,000. So definitely we can't, if we do this approach, this is basically big O n square. So big O n square can't survive. That's for sure with 2 into 10 to the power 5 nodes. What else can I do? This DP on trees approach actually comes to the rescue in many ways. What is the basic idea? Basic idea is that you have got a complicated tree. Is any tree drawn from us? No. No tree is drawn for us. But we can say, okay, let's take this one. 1, 2, 1, 2, 1, 3, 3, 4, 4. Okay, not this one, this one. 2, 1, 2, 1, 2. Okay, 1, 2, 1, 3, 3, 4, 4, 5. 1, 2, 1, 3, 3, 4, 4, 5. And we have 2, 1, 2, 1, 2. 2, 1, 2, 1. Okay, sorry, it's it's in this order. 2, 1, 2, 1, 2. These vertices, I think we have 3, 4, 5. This is 5. Yeah. Okay. Based on this, how can I choose? If I have to understand the problem, what are my beautiful paths? I can say 1 and this 1. This can be one path basically from here to here. This is one path. Then for this 2, I can say, okay, this is one path. Then this is one path. So I've got 3, 5 also as one path. I've got this path and I've got this path. What else? Can I say this is 2 and this is 2? So can I say the path starting from here and going up to here? The answer is no, because I have another node over here which has the same color as the start and the end. So this condition is getting violated. The third condition, that no other vertex on the path has the same color as the first vertex. So if I basically take this one, then somewhere basically I'm violating that condition, because now 3 nodes have the same color. That is not allowed. The first and the last vertex should have the same color, and that same color should not be there for any other node in that path. So I cannot have that long path, which means these 3 are my paths. Okay. Now the paths are intersecting, but the paths related to the same terminal colors will not be intersecting. You can understand that. How can I solve this problem? If I think in a naive way, that this is one node, if I just think, if I take that example, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2. Can I say that, okay, if I tell me what are the number of paths in this tree, number of paths in this tree, let's say that is P1, that is P2, and if I ask, okay, how many paths will go through myself from one part to the other, or maybe to only one part? Can I say, let's say this occupies P3. Can I say the final answer is going to be P1 plus P2 plus P3? I repeat, P1 is basically the number of paths, the answer in this left subtree. P2 is the number of paths in this right subtree. So P3 is basically the number of paths that include this root node and proceed into either the left or the right subtree, or both, or maybe multiple subtrees can be there. So a path that goes through 3. So path that is only in the left subtree is P1, only in the right subtree is P2, and which passes through this 3 is basically P3. Can I say the final answer of this entire tree will be P1 plus P2 plus P3? Let us see over here. What are the answers? No, 1, 2, no, 2, 1, 2 is basically the order. Is it? Is that the order? Okay, sorry. 2, 1, 2, 1, 2. So let us draw it there. So this is 2, sorry. This will be 2, 1, 2, 1, 2. Now based on this, what can I say? From the left half, can I say P1 is equal to 0? No path is possible. P2 also, over here will be 0. Over there nothing is possible. Now I'll only focus on this 3. I can say, okay, I have to be a part. So from the left, I know there is one node with 1, another node with 2. From the right also I know one node is 1 and the other node is 2. So I have that count from the left. From the left I have a count that, okay, there is a node with color 1, there is a node with a color 2. From the right I have that count. There is a node with a color 1, there is a node with a color 2. Can I say, okay, I have 2, so if I have 2, that means with 2 nothing can come from my left also to a right with that 2. If your current node has a color of 2, then you cannot start something over the left with 2 and go to the right with 2. You cannot do that because this 2 cannot be there in the between. So you have to say, okay, do something. If I am 2, look to my left, how many 2's are there? Let's say there are x 2's. Can I say that, okay, that means from each of those x, there can be a path to me. From each of those x, there can be a path to me. So I'll have x answers from the x2's that are present in one subtree. If I have y2's present somewhere in the right, if I have y2's, can I say that I can have y answers including this node and any nodes in the right? Yeah, so for 2 I can say, okay, include involving me. For 2, the answer is the number of 2's in left plus number of 2's in right. Number of 2's in children, or in subtrees actually. In subtrees. The summation of that, right? The summation of that. In a simple way. And if I ask about 1, okay, I am not 1, so can I say that for 1 it will be, just take how many 1's are there in left subtree multiplied by number of 1's in the right subtree, because each 1 in left subtree can pair with a 1 in the right subtree, right? So if I have something like this, let's say I am at a node which is colored as Ci is equal to 3. In the left, let's say I have one, there are 2 nodes with 1, there is 1 node with 2, and there are 2 nodes with 3. This is in the left. In the right, let's say I have that for 1 I have 3, for 2 I have 2, for 4 I have 3. Now what can I do? Can I say, okay, for the 3, for this 3, you can have paths from there to here. So basically that gives us 2. Then for 2, you can say for all the 2's in the left to all the 2's in the right, the total number of paths will be 1 into 2, 1 in the left, 2 in the right, so 2 different paths. A source and a destination defines a path over here. So if I fix the source and if I fix the destination, that gives me a path. So the number of paths is basically going to be number of sources into number of destination in this case. If I say 1 to 2 and 1 to 3, I can say, okay, 1 is present twice and 1 is present thrice in the left and right. So okay, I can say, okay, take any of the 2 in the left, any of the 3 in the right. So by taking them, you basically have 2 into 3 is equal to 6. That's it. And for the 4, I have 3 in the right, but I have nothing in the left. So I will say, okay, I can't join them that way. I can't take that 4 and do anything meaningful to my left. So leave them alone. That's the kind of approach. If I, let's say, if we have 4 paths inside the left, 3 paths inside the right, then overall I can say that my answer will be 4 plus 3 from the children plus through myself, through this root, the answer is 2 plus 6 plus 2. That is 10 plus 7, that is 17. So what am I doing over here? I'm basically saying that the answer at any vertex V is equal to sum of the answer of the children for every child plus some extra value computed from the frequencies. Some extra value based on frequency of colors in all the children. So what do we find over here? That the answer at every level depends on the answer at the smaller levels. Now this frequency of colors we can maintain. How can we find out the frequency of colors in a certain subtree? In this subtree, what is the frequency of colors? And now we only are focusing on such nodes which don't have an ancestor up to here, which don't have an ancestor with the same color. So if I have some color 3 over here, and if I have another color 3 over here, and this is going through that to this top node, I'll not count this one. So we can take care of this edge case separately. For the time being, how can I find this answer? If I know, let's say, I know the number of 3's up to here, and if I know the answer of number of 3's up to here, can I find out the number of 3's up to here? Let's say I know the number of 4's up to here. Let's say there are 6 4's up to here, and there are 3 4's up to here. Can I say in this overall tree, can I say this also will have a frequency kind of thing, that okay, 4 I have 6 plus 3, 9 number of times in my tree. My left contains 6 times, my right contains 3 times, so overall I contain 9 times. So in this way, the frequency values also can be computed from the children. So I can say something like this, that frequency at V for a color C is equal to the summation of frequency of child, or let's say X on C, where X belongs to the children of V. This summation, if C is not equal to the color of V. If it is the color, then I can say 1. If C is equal to A of V, I can say 1. A of V. I will say okay. Why 1? Because if I am, let's say this node, this is 3. So this will say okay, up to here you can get only 1 3. Why? Because all these 3's inside will not be able to form a path going through that 3. That 3 will prohibit it. It will say, okay, under me, no 3 can make any path now through me because I am 3. Make a path with me, fine. But when I'll give my ancestor that, hey, this is the number of 3's, I'll give only myself because they can form a path of 3 if they want, terminal 3. If they want a path of terminal 3, they can't pass through me. I can't be an intermediate node. So if it passes outside saying that there are other nodes with color 3, then basically we are saying this kind of path will be possible up to some other 3, but that is not possible because this node cannot be an intermediate node with the same color. So this will say that only there is one node with 3, that is itself. So if it is same, if this color, basically the color on which we are forming, it is the same as the color of this one, we will say 1, otherwise we will say this. So what have we got? We have got something like this. This is the frequency evaluation of V vertex based on all the child vertices. This is also a DP, and then the answer is left. The answer of V will be equal to the summation of the answer of all the X, where X is a child of V, plus based on the frequencies, I can say for all the colors which are in I can say the smallest set or something like that. So basically the colors which are present in at least one of the children. I can say for all those relevant colors, I can do frequency of something like this for all the C that are relevant. I will go through all the I in children of V, and for all the J in children of V such that J is not equal to I, and I'll say something like this: frequency of IC multiplied by frequency of JC. So what we are basically saying is uh, these are our DP states, basically this answer and this frequency. So as I mentioned, this is a slightly hard problem than the simple problem we discussed, but you can see it's along the same lines. These two answers can be formed easily from those answers. If you know these answers, it can be easily found. Now, how many values will this be? It will be a lot of interaction. Will this go to n square? Slightly not, because in the left, let's say you have some x1 nodes. In the right, you have some x2 nodes. Okay, for x1 nodes, let's say you know what is your frequency map, f1, let's say. In x2, you know the frequency map is f2. So, now the thing is, if in f1 you have 1000 elements, in f2 if you have only 2 elements, then for combining them, you can say this might cost a lot. This might cost 1000 1000 different colors you might need to compare. So there is a trick over here. We say that we can choose a smaller one. We use a technique for choosing the smaller one. We will say, okay, only these colors I'm interested in for the moment. For the path up to here, there is only one color. So this color I will take separate care of. If this color is present somewhere, I will take a look at it. I will maybe form a path if necessary. But otherwise, I will focus on only these two colors, not on these 1000 colors. Let's say the colors are X and Y. Then I will only say, okay, for only, or let's say C1 and C2. The colors are C1 and C2. I will say, okay, for C1, check the left. For C2, check the left. That's it. And now when we have to form the set, will we again form a different F dash frequency map of 1002 elements? 1002 or 1003 elements? Minimum number of elements will be 1000 and maximum number of elements will be 1003. So, will we again form a different frequency map for 1000 or 1003 elements? No. We can just say that, hey, you have already 1000 elements over here. Within this only, you can merge these things. So this is an optimization that I used to make this solution pass the test cases. If I use so much, let's say if you have a skewed kind of a tree, something like this, it is continuously growing. What happens? From here you have passed something, now you again form a map into which you are including that. Then you again form a map over here into which you are including the same thing. And again a map to which you are including the same thing. If you do like this, it will be a huge cost over there. If you have one node over here, one node over here, for including that you have to form a separate map and include everything from here, maybe 1000 elements, and only one element from here. Instead of that, what I'll do is I'll say, okay, just copy the bigger list. From here to here, copy the bigger list. Copy by reference maybe. Copy by reference. And into that reference, into that thing that you have copied as it is, you can copy this smaller number of elements. So basically the bigger lists, you can keep them as it is, you can keep rolling them towards the top as it is, and the smaller ones you can keep on appending. That can be mathematically shown that will solve most of your problems because of the mathematical properties there. So if I look above, over here I can say, so it can be mathematically shown that that number, the total size of the list that you are newly making, that will be somewhere around n or n log n, that can be shown easily. But this technique can be used and very easily implemented. I'll show my own implementation. This is a very this is such a technique that I have quite often used. Many good computer programmers have used this in their code. This is known as merge small to large. Another good place I've used it is in last year's FB Hacker Cup, where I scored in the top 2000 and I got the t-shirt for that thing for the third time. So in that, I think the last problem that I solved this year or the previous year, I think the previous, not 2023, it was probably 2022. That was the time I got this problem, last problem that I actually solved. So yeah, using this, and you can see all these, this is the expression, this is the TP on trees recurrence by which I solved this problem. It's a simple recurrence. If you look at my code, this is what I've implemented. So let's take a quick look at my code. Yeah. So this is something that I submitted in the live contest. So I did not think in 10-20 different ways and code it in the best way. I just did what seemed to me the best at that point of time. Okay. Over here, I'm passing back an answer. What is this answer? Basically, that frequency information. That is a custom pair. See, if you look at my implementation of custom pair, this is it. So I have this hash map which stores the frequency count of every element. And I have this long A, which is basically the answer. Now, this is a basic constructor. I'll go back to my implementation. Okay. This is the DFS. Up to here, it's the same thing. I've created the adjacency list and I called the DFS. Much like the code that I showed you for the previous problem, I'm calling a DFS on one root. What is that root? 0. You can call on any root. Instead of this, you can place any number from 0 to n-1. That is always going to work. I can show you by changing this value, it is going to work. Now, over here, vis of v is equal to true, the same kind of thing, so that I don't visit the parent. This is where the same kind of check is coming, that don't visit the parent. If it is visited, don't again visit it. What is this? This is basically a new frequency map. Now, I'm not going to populate it always. You will see that fun over here. First, I'm saying, hey, call the DFS on the child, first child. Okay, we have entered a loop. On every child, we'll call this. So first child will return us some custom pair. What will this P value contain? The P contains one long value and the hash map. What is that long value? The answer that we discussed. So we discussed two things, right? This is one thing. For all the colors, frequency of V. So frequency of V0, frequency of V1, frequency of V2, these values in the hash map. So freq is a hash map. And ANSV, answer V, is going to be that long value. So I'm storing both of them in those two variables, p.a, p.b. So p.a, I'm adding this to my answer. Why? According to this logic, I'm adding this to this answer. Answer of v plus equals to answer of x. So I'm doing the same thing over here. In my answer, I'm adding this p.a. Next, if p.b contains key CV, what is this? Color of current vertex. So I mentioned it, right? That if this color matches, not this one actually. So if this color matches for this particular C, we will count the matches from every child. That okay, if there are few C over here, from each of them there can be a path to this C. Similarly, in the right as well. So the same thing I'm doing here. If it contains CV in p.b, p.b means that in the child's frequency map, if I have this element, then count how many times I have it, get CV, and add it to my answer. Next, I will have a hash map. I will basically collect that in a hash map p dot b because I have a lot of things to do, frequency 1. And now I'll do the interesting thing which I mentioned, that if frequency 1 is basically greater than frequency, if FRE1 is greater than FRE, which means I should copy other things into FRE1. So if this is not satisfied, that means FRE is the greatest, then I'll copy everything into FRE. So that's what I'm doing. I'm iterating into the other one and I'm copying into FRE. Into FRE I'm copying it, but so I'll iterate the the smaller one and append into the bigger one. That is what I'm doing. Got it? Merge small to large means I will iterate the smaller ones and I will merge into the bigger ones. So that is what I'm doing. I'm finding out the smaller one. So if this is not the case, I will say that FRE1 that means is smaller. So I will merge FRE1 into FRE. That is what I'm doing. I'm iterating through FRE1 and I'm going to merge that into FRE. So let us go through this. What am I doing? I'm saying, okay, in FRE1, whatever key is there, if that key is equal to that color of the current vertex, then don't do anything because that has already been done. You can't use that color. If it is not the case, then follow this particular snippet. If that other larger map also contains U, then multiply it. Multiply the counts. Multiply the counts over here. Answer plus equals to multiplication of both of the counts. And then add them over here. So what am I doing over here? For U, I'm basically putting the count in U plus the count in FRE and the count in FRE1. I'm adding that into FRE. So whatever are there in FRE1, even if FRE doesn't contain that, I will finally count the summation and put that frequency into FRE. In FRE, I'll have everything. FRE is the final thing that I will be returning. This is my final array. Now, if in case my FRE1 was bigger, then again would I iterate in FRE1? No, I will iterate in FRE. For that reason, what I've done, I've just swapped it over here. I've said, okay, if FRE1 is bigger, then swap them so that FRE is bigger. And now for FRE, I will again do the appending from FRE1 to FRE, the same thing. So what do I have basically in FRE? That is my global variable or the variable inside this function. FRE is basically the thing I'm maintaining for my function for this current node. This is the list of elements. If there is a bigger list that comes up in any of my subtrees, I'll just take that and copy the things of FRE into that and I'll treat that as the FRE. This is what I'm doing. Okay, so that's it. You can see what I basically did over here was that don't take all the responsibility for a traversal and keep on roaming and try calculating things this way, that we keep it simple, keep it recursive. You can see in a recursive ways we could solve this in quite an interesting, quite a neat fashion. So this is a strategy basically, that delegate tasks to the sub problems, get tasks out of them, and your task is to basically combine them. So it's basically that thing: divide, conquer, and combine. You are dividing the tasks, getting some tasks solved, and then combining them. So this is one such application of DP on trees. Finally, what am I doing? I get this answer. I will just print answer.a. That is the maximum. That is a total. That is a total number of paths. And how is that formed? You can see answer basically is formed by adding all these p.a's and all these p.b.get cv, all these things, and also over here. Yeah. So adding the answers from the subtrees, then adding the paths whose terminal has that color as the current vertex. Then for the other cases, that if the current vertex doesn't have that color, then add for two different subtrees, and you will actually end up forming pairs or something like this. So let's say if you have multiple, if let's say for this V you have multiple children, over here you have something, over here you have something, over here you have something. Let's say for a certain color, for color C you have X, for color C you have Y such nodes, for color C you have Z. First, let's say I'm reading this one. In my frequency currently, in my FRE, currently let's say my C is, for C there is nothing. There is no such C. What would I say initially? I can say this becomes our frequency array. Frequency array, this one can be a frequency array where C is X, like this will get swapped with this one. Okay, for C we have X. Now when this one is read, we will have that kind of computation that, okay, X into Y gives us, this is what we have in answer plus equals to this. Next, what happens when I include this in the frequency? What happens then in frequency? I will get for C X plus Y. If I combine this into this one, I will get X plus Y. If I do the other thing, it will be Y plus X, same thing. Next, when I bring this one, what will it do? It will say, okay, C is matching. So it will be X into Y plus this thing, X plus Y multiplied by this value Z. Okay. So what will we have? We will have xy plus xz plus yz. Can you see? We have found all the pairs. We don't have to worry about all of them separately, as we are accumulating in our frequency map continuously. Okay, and after this process, I'll basically come and add a z over here. And then move on. So this x plus y plus z I'm going to return from here. This x plus y plus z. So even if I have more than 2 subtrees, that is not a problem. That is what I wanted to show through that example. So hope you understood, hope you got some idea of this topic. There are many other problems as well. Definitely you will find that are, so if I open contests, I'm sure you will find other problems which are based on this technique, which I've recently solved. So let's maybe open this one. Problem number D. N intersections, simple path. Yeah. Any simple path contains no more than 2 dangerous intersections. Let me take a look. Yeah, I think here also there was such a technique in use. Let us see. Yeah, you can see I have used DP states over here. So you had something like that, 2 or whatever. So I formed these different states of 0 such, 1 such, and 2 such, something like that. In the problem, it was mentioned that no more than 2 dangerous intersections. That means up to 2 was allowed. So whether you have 0 or 1 or 2, I have formed in that manner. So you can maybe solve this problem. You have my solution here. You can maybe try solving this problem. It looks a bit big, but it actually isn't big. I actually did some wrong computation here, and I just commented that. But actually, it will be quite simple if you do it. This was in a live contest, so when I make mistake, there is not so much time that I can totally make it neat, etc. But this is a good exercise. You can also you will also find other problems on DP trees recently. Maybe in the next few videos, I'll shed light on a few more such problems, which will be maybe less difficult or more difficult than this. Let me know how you felt this. This is a very important topic of computer programming. I hope you found this session interesting, and if so, then let me know. Please share with people who might find this informative. That is the only major thing I'll ask for. Apart from that, yeah, do let me know through your likes and subscribes as well that you are enjoying the content. So yeah, take care, keep coding, and see you in the next contests. Goodbye. By the way, for these previous problems, I might make separate videos. The problems A to D of this particular contest, which I solved during that contest. I can make a separate video that will probably be a compact video because that won't take so much time as this video. So yeah, stay tuned and see you in my next videos. Bye.